How are you doing?
Good. How are you?
I'm good.
Great.
Yeah, thanks for taking the time to join me today. Okay, so I'll introduce myself. I'm Ivanka. I'm a high school student. I'm a senior this year, and I'm really passionate about climate and sustainability. And I first got really interested in methane emissions when I did my research project at the University of Minnesota under Dr. Joe Hoishley. And then I also did a summer project under Dr. Methane at Cornell. And then I started this initiative, MethaneMatters, to educate people about methane emissions, mitigation sources, and like their impacts. So I also have written, where is it? I wrote this book about methane emissions that goes into way more detail than any of my videos on this YouTube channel do. Yeah, and I'm really excited to have you on the podcast to talk all about methane emissions too.
Thank you. Thanks. It's great to be here, and I really, applaud your efforts to bring attention to the lesser known climate pollutants. And my name's Desiree Plata. I am the School of Engineering Distinguished Professor of Climate and Energy at the Massachusetts Institute of Technology. I'm a geochemist, and so my expertise is following molecules around the Earth system, and I have a particular expertise in industrial processes and materials.
Okay. Yeah, okay. So we'll get into questions. Could you tell me about your educational background and kind of how you got started?
Yeah, sure. So I think, how did I get started? That's a great question. I mean, like you, I got interested for sure in science at a pretty young age. It was really my fourth grade teacher who made me aware of like planetary needs and thinking about being a good steward of the Earth system. And I had excellent middle school science teachers that continued on through high school. I had two really key high school science teachers who pushed me to work hard. My chemistry teacher, of course, would give me lots of extra homework to make sure I knew that I wanted it, which is great that I was really prepared for college at that point. and then an ecology teacher who actually helped me do my first research project by taking us out into the woods and letting us choose an ecological research project that actually pulled on local history and social science, as well as the chemistry, biology, and kind of the forestry subjects that we were tackling through the ecology class. And so
that's cool.
It was really fun. Yeah. And then I'm happy to talk more about my college and graduate school experience and kind of my path that led me to this.
Mm-hmm.
Yeah, so I ended up going to Union College in Schenectady, New York, and Union is famously close to General Electric, and it's a liberal arts school. And so what was cool about that was that there's this major emphasis on research, and lots of the industries in the area would kind of provide resources and tools to the undergraduate researchers at Union. And so I got to do all of this amazing hands-on experimentation as an undergraduate, which I didn't recognize was rare at the time, but I contributed to 3 scientific publications like by the age of 19 or 20, something like that. And again, just thought this was something everybody did. And then later in life realized that was a really exceptional and cool experience. I didn't know that being a researcher was a career path before that. I thought, like many kids in STEM, you would just be a doctor if you liked science and math, when you grew up. And so I was, came into school kind of on a pre-med track, into college on a pre-med track, and then realized, oh, I can do research for a living. Like, that sounds awesome. And wait a minute, I can go to grad school and somebody's going to pay me to go to grad school. And that just like blew my mind apart because, when you're faced with paying for medical school versus paying for or getting paid to go to graduate school in STEM, it's a huge big difference to what the next like decade of your life is going to look like. And the finances wasn't really the thing that I was most focused on. I think what I was focused on was that there was this real curiosity deep inside me to figure out how things worked and how we could make the world better by understanding how things worked. And so for me, once I figured out that a PhD was a thing, I was kind of all in. And the real challenge I had going from undergraduate to graduate education was figuring out if I was going to get a degree in chemistry, the thing I had been studying for so long, or in some more earth science focused field. And I actually, my PhD is in oceanography, chemical oceanography specifically. And while I was doing oceanography, I was studying contaminants that had been released out into the world. And that was great. Some of the work we were doing was informing legislation, but I felt like I wasn't going to, protect anybody from getting sick or impacted by these contaminants. And I really wanted to be part of preventing environmental damage if I could. And so because I was at MIT in the Woods Hole Oceanographic Institution, I was able to go poking around the different departments at MIT and say, what are you making and how can I help you make it better? With the earth in mind, actually, which isn't something that's traditionally taught in engineering and innovation. We focus on cost and performance, but we don't often think about the earth system. And so the rest is history. I've kind of made my life helping engineers and big industrial processes develop with environmental considerations in mind.
Yeah, that's interesting because I didn't really realize that research was a career path either until I did my research project.
Yeah, it's amazing because it's kind of how we make new knowledge, and it's this hidden part of society. Even the ability for your cell phone to take video and store it on your device. That's something that came out of an academic lab. The transdermal medicine patch that was invented across the street from where I sit. MS-DOS was invented on the other corner, and so was radar. There's all these things that come out of academic labs that people think are happening in industry because that's how they consume them or buy them. And even my mom today, she's like, how come I can't buy anything you invented at Walmart? And I'm like, it's just because our inventions are a little further from the Walmart shelves and in a different market. But yeah, I think that's a really important point for the world to understand, actually, that there are these individuals like me and you who go into the lab and work really hard to build products and processes that actually make people's lives better.
Yeah. And now I have a research paper getting published too, which is so exciting.
Congratulations. That's awesome. Yeah, I want to copy.
Yeah. So can you tell me a little bit about some projects you're doing?
Right now, yeah, there's when I was in high school, a friend of mine drew a little cartoon of me getting hit by a car trying to pick up a can in the middle of the street, and she's like, the girl who tried to save the world. And I very much am like the girl who tried to save the world a little too much, probably. So that's all to say there are a lot of projects going on in my group, and I have an awesome team of mostly graduate student researchers and some postdoctoral researchers and undergraduate researchers, and they work in a few main areas, and all of them really trying to think about changing the way humans interact with the Earth system. So we have a group of people who are kind of squarely focused on methane and methane mitigation. We have another group of people who are focused on other types of carbon removal, primarily through biological agricultural wastes, and what we might do with those wastes to actually take CO2 out of the atmosphere, and thinking through that engineering system. That's a really complex system. But if we imagine a world where we're not extracting fossil fuels, how do we meet all our needs and build a restorative economy? The last part of my group really works on the fate of industrial chemicals, and that includes things like plastics, as well as other small molecules like pesticides, and what happens to them once they get out into the Earth system. And the goal of that work is really to try and understand from a chemical structure alone what's going to happen to that material when it gets out into the earth? Is it going to make anybody sick? Is it going to end up in the soil or the sediments or the water or the air? And what's it going to turn into? Like, what are its transformation products? And if we can answer those three questions, then, and if we could do it fast, it would actually really transform the way that humans and chemistry interact with one another from an industrial perspective.
Yeah, that's exciting.
Yeah. I'm guessing you might know more about methane.
Yeah. We can talk about the other stuff too.
Yeah. So with regard, do you want to hear more about the methane project and what's?
Yeah, let's do that first.
Yeah. So my group, let's see, how did I come to this this problem? I guess I was studying hydraulic fracturing, and so in about 2008 in the United States is a real marker for the oil and gas extraction boom domestically in the United States. And that was due to a legislation change that also converged with this technical innovation that allowed us to do what's called horizontal drilling with hydraulic fracturing. That involves the use of a whole bunch of industrial chemicals. And I thought, aha, this is the research project for me. I'm going to go see if I can find these chemicals in drinking waters. And so we really heavily studied the impacts of hydraulic fracturing in domestic drinking water supply. And it turns out that you only really see those impacts from the waste associated with hydraulic fracturing and from spills, like big accidents, which always happen in industry. The thing that I didn't necessarily anticipate was that one of the first molecules I found in drinking waters in this region was methane. And it became really obvious that methane was being emitted not just from oil and gas extraction, but really lots of dilute places all over the Earth's surface. And I started thinking about how we would actually destroy methane in order to kind of undercut its global warming potential. Do you know what happens to methane in the atmosphere? What its main reaction is?
Not really.
Yeah. Okay. So the fate of methane released to the atmosphere is to become CO2. And it's on about a 9 to 12-year time scale. So about 10 years. Yeah. And so, yeah, and right, it gets oxidized, as we say, to CO2. And that's the reason that methane's global warming potential gets lower and lower through time. So you'll hear people say it's 80 times in the first 20 years, and then it's only 25 times over 100 years. And that's kind of confusing to people, but that's because it becomes this less powerful warming species, right? It goes from being methane to being CO2. And so the technology that we really wanted to develop was one that accelerated that process. So take those dilute methane emissions that are coming out all over the Earth's surface and get them to turn into CO2 faster. So we started to look at ways to do that. And as someone with training in oceanography, I knew that there were bacteria that could access methane that was present at really dilute levels in the presence of oxygen at atmospheric-ish conditions, so not super hot and not super high pressure. So kind of like the conditions you need if you're going to treat low-level methane that's coming out of the Earth's surface. And those are called methanotrophs, and methanotrophs or methane lovers like to react methane into, the first step is to make it into methanol, and they can generate energy from the rest of that process or turn it into biomass. And so we wanted to mimic that chemistry. And that chemistry is one that's really what we say is highly conserved around in all the organisms that can do that chemistry. The way that they do it is almost the same in the protein. And the protein has a couple of metal atoms in it, and they're almost always a whole bunch of coppers. Sometimes they're a whole bunch of irons. And so we were like, great, we're pretty bad at making proteins. Like my personal self and my group didn't really know how to do that. We're like, okay, what are some other, and we knew it was expensive and that those proteins wouldn't be stable once we took them out of the organism or brought them into the air. And so instead of doing that chemistry, we read about these materials called, they're clay aluminosilicates or zeolites. And take a zeolite, it has these nanoscopic pore spaces, very much like the pocket of the protein that does this special chemistry. And we doped some copper into those pore spaces and tried to see if it would react low levels of methane in atmospheric conditions. And it turns out that it worked. And we were
Yeah,
really
that's cool.
yeah, it was a super exciting result. And so ever since, we've really been trying to see, what does it take to kill the catalyst? Can we use it in dairy? Can we use it in coal mines? Can we use it in the natural gas supply chain? What are all the opportunities for reducing low-level methane emissions out in the industrial world? And can you do it in a way that makes kind of economic sense?
So have you tried it in livestock or coal mining or these other industries?
Let's see. Yeah, we've been to a bunch of dairies. I've become
Okay.
well versed in what the inside of a dairy barn looks like in the United States. And so we've been to lots of industrial scale dairies across the US to actually learn more about the composition and the atmosphere there and to see if our catalyst works in that air. And it does, right? Like it can destroy the methane. The problem, which I think is really important for anyone inventing a climate facing technology, is that it actually takes a little more energy than makes sense. And I'll try to explain. So our catalyst is a thermal catalyst, and it means you have to warm it up. You warm it up a little bit hotter than like your cookie oven. So it's not crazy hot like some industrial processes, but it's hot. And so in a dairy barn, there are these big fans that ventilate the air, and they're serving a couple of purposes, like keeping the particle load down, cooling the animals, and keeping the ammonia levels down, right? All those things are kind of, unsavory to breathe, and we want the cows to be happy. So animal husbandry and happy animals is like the top priority.
Yes.
You're moving a lot of air, and it turns out that you move somewhere between 1 and 10 million cubic feet a minute in some of these industrial dairy barns. Now that's like, 10 tractor trailers going past you in 6 seconds. It's a huge, large quantity. And you have to get the methane out in an instant. Heating up all of that air takes a lot of watts, right? A lot of joules per second. Now, if there were a lot of methane in the air, methane, when you turn it into CO2, that's an exothermic reaction. It generates heat or energy, gives it off into the ambient. And that's why we use methane to heat our homes, right? Convert it to CO2, it releases heat. Now, in a dairy barn air, because you're moving so much air, you're diluting the heck out of the methane. So it means pack it, you're not actually getting a lot of heat. Now, that means our reactor would have to be plugged in, as it were. Really, you would probably just burn propane or natural gas to keep it warm. And when you do the math on it, it doesn't make a whole heck of a lot of sense. You'd actually be causing more CO2 emissions than you would be abating on the equivalent if you were going to use this type of thermal catalyst. And so, of course, we're committed to helping the earth, and we don't want to do that. But if you use the catalyst in a coal mine, that's not necessarily true. So coal mines have a slightly higher level of methane. And what that means is that we warm up our reactor once, and then the process starts to drive itself. You get your carbon abatement for free, or your emissions reductions for free, because that exothermic reaction actually drives the whole thing. And that's really cool. And we're excited to be field testing that in the next year or two.
Okay. Yeah. So I did my research on reducing methane emissions from enteric fermentation in cows. And it sounds like that could be like a better solution than converting it after it already gets released.
Yeah, I think it's a better solution for a couple of reasons. One is that a lot of cows on planet Earth don't live inside. And so you could really never treat the air flowing past an open pasture. You really can only do kind of post-release technologies when the animals are living indoors. And dairy is one example of where they are living indoors, but they don't do that for beef production, and in much of the transitioning economies, of course, all of the animals are outside. And so food additives represent this opportunity to stop the methane before it gets released from the cow's breath. I think the challenge with food additives is really to make sure that you have a food additive that maintains the animal's health. And you know already that listeners might be intrigued to know that there are some food additives that actually damage the health of the animal. They certainly work to make less methane, but it's because the animal is sick, not because it's interrupted this biochemical pathway. And so so it's important to make sure that you do, you know how your food additive is working, and you are sure that it's not affecting the health of the animal.
Yeah.
What kind of food additive did you work on?
I worked on tannins at the University of Minnesota. That's the paper that is getting published.
Great. Very exciting.
Yeah. Very exciting. Yeah. What's your lab composition like? You talked about it a little bit, but who all do you work with?
Yeah, who all do I work with? You mean demographically, their identifiers and stuff? Or
I mean, in general, what backgrounds do they come from?
Oh, yeah, what a nice question. Yeah, all over actually. So a lot of I am in a civil and environmental engineering department. And I have maybe once in a while, I'll have an environmental engineering undergraduate student. More often, I will have people who are chemists, chemical engineers, mechanical engineers. Sometimes I'll get a microbiologist, and I think that's it. I've gotten some geoscientists as well. So, and material scientists. So my group composition is actually really diverse, and from an intellectual background perspective. And I think that that's great for lots of reasons. The first I'll talk about is that in order to do environmentally sustainable design, right, like making new materials and processes that are actually going to be beneficial to the Earth system and not detrimental, you have to be able to talk across disciplinary boundaries and kind of understand, what do I value, what do you value, what's the common denominator or the translator that can help us kind of get all of our objectives aligned, if that's even possible. And so speaking across disciplinary boundaries is kind of a first order need. It means that the research can be slower for sure, because we got to get everybody on the same page. And there's a little more of an induction period, an uptick before the research really takes off. But I think the product that you get in the end is kind of differentiated, totally unique, something that you wouldn't have thought of without both of those pieces or all of those different elements. So that's reason number one. Reason number two is that the environment, it doesn't work on the basis of physics or biology or chemistry or math in isolation, right? It's an integrator of all of those things. And so if the Earth system really requires you to have that breadth of understanding along with the depth, so you have the good fundamental science, then we need to have kind of all of those people in the room.
Yeah.
So maybe the third reason that it's a real asset is that this type of stuff that we do is difficult. We're often building our own equipment and writing our own data processing algorithms for handling the big data sets that we do. And so this means that most of my students who come actually have to learn a little bit of electrical engineering on top of whatever their background is, and they have to learn a bit of data science. And I actually think that's really important.
Do you have any people that come specifically from data science or machine learning or anything?
Most of my recruits do not come with any amount of data science or machine learning knowledge. They might have used R or Python in a class as an undergraduate. Some of them have used GIS, like a geospatial software, but very few of them come already knowing what they're going to need to know. And so it's the only thing that I require of all of my graduates. Our program, of course, has requirements, but I require all of my graduates to take some kind of data science class, preferably in the context of earth science, of course. But they have to know how to program and read code and use those things. And so we do a lot of machine learning, or some fraction of my group does a lot of machine learning. Everyone is kind of asked to generate fairly large data sets so that we can interpret them in a different way beyond what you would normally be able to do.
Yeah. So what kinds of technologies do you use in your projects, like sensors or devices or anything like that?
I was joking to one of my students, we should make like a little YouTube video of all the, basically like anything you want to measure in the world around you, we can do really well. And so, and I wouldn't say, there's a lot of people who are going to make that claim, like I would back it. I'll bet money on it. So we've got kind of all the toys. And so if you want to measure metals or organic compounds or in the air or the water or the sediment, like we've kind of got everything. I can tell you what we use for our methane tools.
Yeah.
But we feel very fortunate to be able to make those measurements. And again, the reason being we're interested in industrial chemicals in the natural world, so we need a lot of that. And we've got, we're kind of in a science candy land at MIT, and so that's just awesome, and I can't recommend it enough. The methane tools that we use are multifaceted. So we have a gas chromatograph, kind of the old school way of measuring methane, and that has a flame ionization detector on it. So it burns the methane and tells you how much methane is in that sample based on the flame intensity.
I used one in my research.
Yeah, awesome. That's the number one method. You always know your GCFID is right as long as you're calibrating it. And so that's ground truth. And then the second tool that we will most often use is something called a Picaro cavity ring down spectrometer. And have you heard of those before?
I don't think so.
Okay, so the thing that makes methane a greenhouse gas, of course, is its absorption of infrared radiation. Just like CO2 has the same, I say molecules got the wiggles, right? So these vibrational and rotational modes means they absorb in the infrared. And so this tool actually takes advantage of that principle. But the challenge is that at atmospheric levels, methane's really dilute. So for every million molecules in the air in front of you, how many are methane?
Ooh. 3.
Well, it's 2. It's like 1.9. Yeah. And so, but it's about 2. And how many CO2s? Do you know that number? It's a harder one.
Probably more.
Yeah, 420. Right, so
okay.
But it's still pretty dilute, right? 420 out of a million, or 2 out of a million if you're trying to measure methane. That's not a lot of stuff. And so there's this law called Beer's law, which tells you that you'll get more absorption through a longer path length. So the way the cavity ring down spectrometer works is it actually has a series of mirrors. And so for a small box, you can get a really long path length of light. And so it's trying to encounter as many methane molecules as it can to get that absorbance to say, aha, this is how much methane must be in this sample. Now, the cool thing about cavity ring down spectrometers is they can actually tell you if you have methane with a C13 isotope in it or methane with a C12 isotope in it. And that gives you some isotopic information, which can tell you where the methane has come from. Has it come from a thermogenic process like natural gas, or has it come from a biogenic process like a swamp or a lake or the guts of a cow?
That's cool.
Yeah, it's pretty awesome. And then we also invent some other sensors in our lab. So I'm happy to talk about those if you think time allows, but low cost sensors that could be used at the ground base to help people get a sense of how much methane is coming out of their source and from where.
Yeah. So I have time, but do you have to leave at a certain time? Or
I should, but I'm happy to. I get very excited about these things.
Okay, yeah.
Well, let me share what we're doing with low cost sensors, and this involves a couple of amazing researchers, in colleagues that I have. So let me first ask you have you heard of the company Theranos? Remember the young woman from Stanford who wanted to measure all these molecules in a drop of blood?
Oh, I think I might have heard something about that. I don't know the details though.
Well, let's forget that. It didn't work. It kind of famously didn't work. And analytical chemists at the time could have told you that, right? Because there's just not enough stuff in a drop of blood to get all of those measurements. So that was like thing number one, right? There was no single molecule detection at the time. And even if there were single molecule detection, sensors are actually pretty bad at responding to only the thing you want them to respond to. They're often experiencing what's called interference with other things. So you want to hear a secret about pH meters?
Sure.
Okay, you know pH meters, you stick it in the water and it tells you the pH. They actually respond to like all cations, right? Ion selective electrodes in general, if you have a potassium meter, it's going to read potassium, and it's also going to read H+, what the pH meter measures. It's also going to read ammonium ion. So it's responding more generically to cations and the other ones that are supposedly selective for anions are doing the same thing. There's no fighting interference in sensors. And so a colleague of mine, whose name is Amy Miller, she's a professor at Northeastern University, invented a technique when she was a young graduate student to actually say, okay, we know all these sensors interfere with each other. Let's build them up in a matrix. And now feed them different solutions and let them interfere. And we can watch their signals and say, now let's use some simple machine learning algorithms, or what are called neural networks, to back out their interference patterns. So in other words, let them interfere, watch how they interfere, and then use a little bit of computer science to take out that interference signal so you can know what was really the signal from H plus itself and what was really the signal from potassium ion itself. And we're doing something very similar with methane right now. So a colleague of mine, Tim Swager, in the chemistry department at MIT, has invented these kind of exquisite single molecular detection sensors, and we assemble those with a series of other low-cost sensors in an array. We feed them different atmospheric compositions, and then Professor Amy Miller comes around and says, okay, let's use our machine learning algorithms to try to understand what was actually there based on the different combinations of gases that we fed them in the first place. And we hope to someday use this to be able to get Picaro cavity ring down spectrometer-like performance from an array of low-cost sensors that you can fit in a shoebox or so.
Yeah, that would be great.
Yeah, super fun.
Yeah. Are you collaborating with any other universities or some private companies maybe?
Yeah, that's a good question. I don't know. I mean, we all talk to each other. Science is a really friendly and small space, which I hope you got to experience in your research. So we all communicate fairly regularly, like among the methane research community. So I've got lots of colleagues, at Stanford and UC Davis, and we try to stay in touch. On the environmental chemical side, we talk to our friends at Iowa State and Northeastern University and other places. And I think that you're always in kind of constant conversation with your colleagues around the academic universe. And we do collaborate with companies. I won't name them here because I didn't ask their permission, but a lot of what we do is oriented towards industrial collaboration in order to help companies solve problems faster, and also so that we can learn about what's relevant to their needs. So that lets us do better work by understanding what their challenges are and what they care about. So I go to like a mining I never thought I would go to a coal mining conference, but I go to coal mining conferences to try to figure out like what would it actually take to destroy methane in these coal mine vents, and that can be really, really fun and humbling, right? Like every human being on planet Earth is really smart and has something to contribute. You just have to like listen and ask them, and that's one of the best parts of my job.
Yeah, that's nice. I also heard that you have your own company. Could you talk about that?
Yeah, I have two. One that's dedicated to methane emissions reduction, and that's called Mox Air. And Mox Air is right now, scaling, like even just a couple weeks ago, breaking ground for our large scale catalyst fabrication. And our hope is that we'll be able to see that in operation and within the next year or so.
Wow.
Probably soon, but yeah. And then the second company is called Nth Cycle, and Nth Cycle, it was a collaboration between myself, Professor Chad Vasitas at Harvard, and my second PhD student, Dr. Megan O'Connor, who's now CEO of Nth Cycle. And Nth Cycle established the first domestic cobalt and nickel recovery facility this year in Ohio, or last year in fall in Ohio, and it's wicked awesome. If listeners haven't checked out nthcycle.com, I really recommend it.
Wow, that's super exciting.
Yeah. I mean, the Earth's not going to save itself, right? And so to get these technologies off of the scientific paper and beyond into the commercial world, if they're going to have the impact that we imagine and hope for them.
Yeah. I also wanted to ask you, what are some challenges that you face in doing your projects?
Well, there are many. Like doing this. I'm not selling a dating app, right, or a food
Mhm.
service. Like, we know, like if somebody's going to use that dating app and use that food service, that's a really easy sell for people. Um, if you're trying to build a thing that never existed before and do it at a scale that impacts the warming rate of the planet, like that's a big, huge undertaking, right?
Yeah.
Really hard for people who are used to investing in a technology where they're going to see a return in 12 months, invest in a technology that might take 4 or 5 years to get off the ground. And so you have to be patient, and you have to be willing to help the people who are putting the resources in, the financial resources in, to see what the potential is, and that there's promise for it to generate a return for them. And so I think those are some of the biggest challenges, right? Like I think the second challenge is there's just not enough talent out there, right? We need, if I could wave a magic wand and get 100 more STEM folks in the door, we would every day, like we would love that. We need a technology savvy workforce. There's plenty of opportunity. There's plenty of need in the world, certainly. And making sure that we have people who can do things with their hands as well as with their computers. Both of those things are really critically needed. And so that's a secondary challenge, I think, is just finding kind of those special sauce in your team. And I'm really fortunate that I have an awesome team. And that is really critical, actually, to getting through those tough moments when you're trying to do something that's never been done before.
Yeah. So that kind of leads into my next question. What advice would you give someone like me or a high schooler who wants to go into a field like this?
Um, don't say no to yourself, right? And no for an answer, right? Like just keep you really have to have a lot of determination and grit to break down those barriers. I think a lot of people will have experience of failure and stop there. We have this joke in tough tech, like you got to fail fast. You've probably heard that before. The more, if you're failing, you're learning. And so kind of just reframing your brain to understand that in research, in first of a kind demonstrations, there are going to be failures necessarily. Like if there weren't, you wouldn't be learning. I had a friend who was a skier who used to say, if you're not falling down, you're not trying hard enough. And like you really have to become comfortable with saying, I don't know, but this is how I would find out. Or, okay, that didn't work the way I thought it would. What is it trying to tell me? Instead of, I don't know, or I failed, and now I'm going to quit. Right. And so there are points where you should quit, right? Like if you know it's not going to work and you've turned over all the stones, like move on to the next thing, because you're probably uniquely talented and you want to apply yourself to important problems. But don't quit easily. And I would also say that there are so I'm a big believer in the American dream. Like I didn't grow up with a lot of resources, and now I feel like, I have everything in the world that I could ever want. And I did that through, hard work and education. Education is a springboard onto to really any life you want. And one of the most rewarding things about being a PhD advisor is that you can make other people PhDs, right? And so, and they're always going to have access to a lucrative career, like for the rest of their life. And that's incredible. That's an incredible gift to be able to give someone. So that said, I didn't get into a lot of the colleges that I wanted to get into when I was a high school student, and I thought, well, this is it. I work at McDonald's for the rest of my life, which is a fine job. But it wasn't what I wanted. And so I think that understanding, like, oh, I am going to get access to a great education wherever I go is really important. And like in the US, we tell people there's 5 colleges you can go to that are going to put you on a good path. That's bogus. They're like, all the colleges are great. They're all populated with professors who care deeply about your success. And it's really up to you to find those opportunities and take advantage of them. So that's my biggest point of advice. Like take advantage of every opportunity that you have access to where you are. And then you're gonna, turn that into success, and demonstrable success or demonstrable success is what you're looking for. So publish that paper, file that patent, make that product so that you can show it off for your next thing.
Yeah. Yeah, MIT sounds like such an exciting place to be with all your like cool stuff you have and all the people there.
Yeah, MIT's like, I joke, it's after I tell you, you can be happy anywhere you are. It's for sure.
Yeah.
Like, I love MIT so much. And one of the reasons is because of the people. We have a lot of physical resources, but we have like the greatest human resources in the sense that people like the unifying features to me are people are all really hardworking, and they're all wanting to make the world a better place. And when you have like a lousy idea and you say, hey guys, what do you think of this idea? People don't say, that's a terrible idea, go crawl under a hole. They say, that'll never work. But if you wanted to make it work, here's how we would do it. And then everybody's brains like start thinking. And so it's a really lovely place in that regard. And I would say that, it's a place where people are really valued for their ideas. I like to say everybody at MIT really looks me in my eyes and wants to know what I'm thinking. And we treat everybody that way, from, the undergraduate to the senior researcher, to the staff. And so it has this really community oriented feel where we're all really mission oriented and willing to work hard to see that mission become a reality. And I think it really, that's what I would like to see take shape at more places around the world, because we need all those talents at the table.
Yeah. I think that's all the questions I had for you, but do you want to say anything else?
I know, I would just applaud the work that you're doing. I think it's really awesome. And I hope I get to meet you in person someday.
Me too.
Thanks, Ivanka. All right, have a wonderful